Okay, exercise number 6. If G is a group where all elements satisfy that G squared is equal to the identity, then G must already be abelian. We have seen here a special case for order 4, groups of order 4. In this group, every element satisfies this relation, that the element times itself is the identity, and indeed this group is commutative. Now we proved that this is generally true. Such a group is called an elementary abelian group. We'll learn about those later on. We take two arbitrary elements of G and then we show that AB is the same as BA. Okay, our onlyest chance, or the only thing we can use, is actually this relation which holds for all elements. So let's try the following. We insert an identity left and right. This is of course always allowed. And now we write the first identity as b squared. Why would we do that? Because in the end we want to move the b in front, and this is our onlyest chance. So then ab, and here in the end we want to have a, so we write this identity as a squared. All right. So this is true because b squared is the identity and a squared is the identity by assumption. Now what do we get? We get, and as always we have associativity, so I need not worry about parentheses. So we have b times b times a times b times a times a. Yeah, we've just written those here as b times b and those as a times a. Still doesn't look too good, but here we have b times a and here we have b times a again. So in the middle we end up with ba squared. And now luckily BA is also an element of this group, so if I square it I end up with the identity, which gives me BA. And this shows, since A and B were arbitrary, that this group actually is abelian. Now if you just watch this, then you say, well, okay, this is easy, but if you have tried that for yourself for maybe 10 or 20 minutes and did not get this idea, this is actually pretty hard. It's pretty easy to get stuck here with no way out if you don't see these tricks here. All right. Okay, last exercise on this very long problem set number 4. This is, without the hint, actually a hard exercise, I think. So we have to prove if the order of G is even, so the cardinality of the set or the number of elements of G is even, then there exists an element which is not the identity, which satisfies G squared is equal to E. So G is its own inverse. For the proof we follow the hint. First we take this subset of G, all the elements that do not satisfy this. And those are exactly those elements that are not equal to their inverses, right? Because G squared is G times G, and if this is equal to E, then G is its own inverse. Okay, now comes the important idea. If I take an element of H, then it is different from its inverse element. And of course, but the inverse of this element here also lies in this set, because its inverse is G, which is not equal to G inverse, right? So G inverse also satisfies this condition here. So I can always pair pair the elements of H up. So H can be written in this form. Possibly H may be the empty set. It's possible that all the elements actually satisfy G squared equals E. Remember the elementary abelian groups, they exist as we have seen in exercise 5. So either H is empty or the cardinality of H is an even number. So if I define 0 to be even, then the empty set is included. But here you see you have 2 times the number of these pairs, so this is an even number. So now we look at the complement G without this set H. The order of this set is simply the order of G minus the order of H. So the number of elements is what I call the order here. But now, by assumption, this here is even. We subtract an even number, so this must again be an even number. But what are those elements? Those elements are the self-inverse elements, so the elements that satisfy G squared is equal to E. And obviously the identity is an element of this set. So it has at least one element, but if its order is even, it must contain at least another element. So we have found another element, G not equal to the identity, with the property that G squared is equal to the identity, and this finishes our proof. So this here means there exists an element in this set which is not the identity, because we need at least one more element in this set, and by definition this G here satisfies G squared is equal to the identity, and this concludes our proof. All right. Whew. That was quite a bit of work. I hope you could solve most of the exercises, or at least part of them, on your own. And I really hope that this video helped you, especially if you're a beginner. If so, please give a like, subscribe to this channel, and I hope to see you many more times. Bye bye.